It's going on page 115. So today we're going to look at areas of regular polygons, but first I'm going to have somebody tell me what makes a regular polygon a regular polygon. And of course, he's not. Really? Oh, she's not here either. Oh, good. All right, Fernando, what makes a regular polygon a regular polygon? Very good. Thank you. You used the right words and everything. Equilateral and equiangular, which means all sides are congruent, all angles are congruent, right? That's what makes a regular polygon a regular polygon. Thank you very much. That is important to know. Now, we're going to actually start by looking at the polygon. We'll come back up and fill these in. I think I want to do it this way here. So this is a regular polygon. I know it's not really labeled as one, but it does tell you that up there, and you'll be told in a lot of this stuff that that's what's happening. To talk about the different parts of this, then we want to think about this being inscribed in a circle. So I'm going to do my best to draw this inscribed in a circle. I know it's not going to look beautiful, and you do the same just so you kind of get the idea. You don't really want it to look like a bubble on each side, but just you can pretend, you know, you'll pretend that that's a beautiful, perfect circle. Okay. So the parts of the polygon, first of all, we have the side, which, you know, it's not really that crazy or weird. And we'll denote that with a lowercase s. As far as the circle is concerned, line segment CD is what part of the circle? The radius. It is also the radius of the polygon, okay? So a regular polygon has a radius. The difference between the radius of a circle and a radius of a polygon is that in a circle, you can draw it in an infinite amount of places, wherever you want, anywhere around the circle. But in a polygon, you can only draw the radius as many times as there are sides. So this specific polygon is a what? Pentagon, which means it has 5 of everything, right? So it has, there's 5 different places you can draw the radius, and that's it. But again, if you think about it, it goes from the center to any point on the circle. Well, in a polygon, it goes from the center to a vertex, and that vertex right there is what actually touches the circle. So again, if you kind of think of it being inside of a circle, it kind of helps you with the terminology there. All right, so then this angle right here in a circle would be called what kind of angle? Central angle, good, because the vertex is at the center of the circle. So we have a central angle, vertex at the center. It's also the central angle of a polygon. And then we also have this point, which is the center of the circle. It is also the center of the polygon. Polygon has a center also. So all of those terms, those are all terms you already knew that you can relate to a circle. No big deal. They exist in a polygon also. Now, this dotted red line segment, CB, this is a new term for you. This goes, instead of from the center to a vertex, it goes from the center perpendicular to a side. This is called the apothem, A-P-O-T-H-E-M. You can also hear it pronounced apothem. I think it's kind of a tomato thing. So apothem is what usually comes out of my mouth. That's what I was taught. So then this is a lowercase a. Okay. So we have a side, a radius, a center, and a central angle, all which should totally make sense to you. The only new term that you have here is the apothem, and it's perpendicular. We all good so far? All right, so let's go back up to the top and let's fill in some of these blanks with what we've already talked about. All right, so the center of a regular polygon is equidistant from the vertices. So instead of being equidistant from any point on the circle, if it's a circle, it's just from the vertices. So you only have as many as you have sides. Okay. Then the new part is the apothem. It is the perpendicular distance from the center of the polygon to the side of the polygon. Then we have a central angle of a regular polygon, has its vertex at the center and its sides pass through consecutive vertices. Okay, so let's go back and talk about the central angle again. because in a circle, angle FCH in a circle would be a central angle, right? Because the vertex is at the center. In a polygon, it's not, because it says that the sides have to go through consecutive vertices. So FCH is not a central angle in the pentagon, but FCG is and GCH is. So there's only 5 central angles as well. Does that make sense to you? There's other angles, but they're not central angles. Okay. All right, so it's just a little bit different than in a circle. And then each central angle measure, okay, so since there's only 5, because there's 5 sides, if there are n sides, how many angles would there be? No. If there's 5 sides, there's 5 angles. If there's n sides, there's n angles, right? Okay, so an n-gon, whatever n is, that's how many sides it is, that's how many angles it has, that's how many everything, right? So all of these central angles together have to add to give me what? 360. So to find each central angle of a regular n-gon, each one, then I'm going to have to do 360, and then what? Divided by n, right? So 360 divided by n gives me one of the central angles in any regular polygon. Everybody good so far? All right, so let's talk about area here. When I get here and I've got this polygon, I've got 5 triangles that it breaks it up into also, right? Specifically, what kind of triangles are these? Isosceles, good. And would that be true in any polygon? Think about that. Any regular polygon, I'm sorry. Yes, because the radius is going to be the same, right? So it's going to guarantee you that you have little isosceles triangles, right? If the central angles are all the same and these are all isosceles, what can you tell me about all these triangles? They're all congruent, right? All the triangles are congruent. So if they're all congruent, do you know how to find the area of a triangle? Yes. So can we find the area of one triangle and then multiply by how many triangles we have? Yes. And so that's what we're, in worst case scenario, you can default back to that if you have no idea how to use the actual formula. It is always, not always, most of the time it's easier to use the real formula, but that's how we're going to come up with it. So we're going to look at how do we find the area of a triangle. So the area of each triangle, I know that and we'll look at triangle FCE. Okay, so we're going to look at this triangle right here. So triangle FCE, I know that the area of a triangle is 1/2 base times height. Right? It's a triangle. And so specifically for that little triangle, the base of the triangle is what part of the polygon? The side. So this is 1/2 times the side length, and then the height of the triangle is what part of the polygon? The apothem, which is A. Okay? So the triangle in terms of polygon stuff is 1/2 S times A, right? So we're going to take this, we're going to do a little stuff with it, and I want you to draw an arrow down to here, because we're going to do it underneath this line right here. So if I want the actual area of the polygon, oh, I don't want a P there, don't do that. All right, so what I want is the area of the polygon. Then, in general, how many triangles will I have in any regular polygon? N, right? In this specific case, it's 5, but I'd have N, right? So N is how many triangles I would have times 1/2 times S times A, right? Because that's N times, that's the number of triangles times the area of the triangle. That would give me the total area of the polygon. You with me? Now, can you multiply things in any order? Yes. So I'm going to mix this up a little bit and make this 1/2 A times N times S. And then I want you to think about just N times S. If I just did N times S in a regular polygon, what would that give me regarding the polygon? The perimeter. It's the number of sides times the side length. Doesn't that give me the perimeter? The distance around it? Okay, so this is the perimeter, which is equal to N times S. Which means then I can make this 1/2 apothem times perimeter. And the P is capital because perimeter is a calculated value. The A is little because that's a length that you could go measure with the ruler if you had enough information. Okay, so that tells me then that my area of a regular polygon important, area is equal to 1/2 apothem times perimeter. Okay, so your area of a regular polygon is 1/2 apothem times perimeter. That is the formula that we're going to use. Okay, everybody good so far? So even though the formula doesn't come flat out and say this to you, but you do need the central angle of each one. So to find the central angle of a pentagon, I would do 360 divided by what? 5. So you don't need your calculator. Don't touch your calculator. What's 360 divided by 5? 72. Good. All right. To find the central angle of a square, that would be 360 divided by what? 4, which gives me 90. Okay, so let's just stop here for a second. I want you to think about what we're doing, and it's different than what we did with some angles before. In a pentagon, I did 360 divided by 5 to get this, which is 72. That's this angle. That is different than this angle, which we did when we did the n-2 times 180 stuff. I actually don't really care about that right now. That's not part of what we're doing. In a square, obviously, this angle would be 90, but this angle here is also 90. So that's just a coincidence. It's not like this angle and the central angle are always the same. You good with me on that? So just be careful. It's different, totally different thing, because sometimes I see people trying to start that. All right, so then the 12 gone would be 360 divided by 12, which gives you 30. So see, finding the central angle, super easy, right? Something that we need to do, but it is super easy to do. Any questions at this point? Okay, let's go on in here. All right, so this says find the area of each polygon. This should say find the area of each regular polygon. I left out that word. That's a very important word, because without that, then we wouldn't have enough information to do it. So the first thing I do is write down my formula. Area is equal to 1/2 apothem times perimeter. So to find the perimeter, that is n times s. Do you know what is n? 6. What is s? 6. It's a coincidence. It's the same thing. Perimeter equals 36. Okay. Perimeter is almost always super easy to find, but write it down, because one of the most common things that I see a lot, and it's usually from the stubborn people that refuse to write stuff down, is that they will do all the other work that you got to do, but instead of plugging in the perimeter, because they thought, I don't need to write that down, that's easy, I can do it in my head, they just put in the side length, and then they're totally wrong. So just be careful with that, okay? Let me take that, because I will totally take that. You can get it back next Monday after school for $15. All right, so I've got my perimeter, and the other thing is I usually get this question asked at the end, like, how did you figure out n? How do we figure out n? We count it, right? It's nothing magical. You count. That's how, n is the number of sides. That's how you figure it out. It's nothing magical. All right, so did they give me the apothem? No. Okay, so then what I need to do, kind of estimate the center there. Draw that in right there. And then this is my apothem. So the solid lines that I drew are what? What part of the polygon are they? The radius. So I want you to write yourself a little note up here that you always draw at least 2 radii. Okay. And I say at least because sometimes you draw 2 in and you're like, I don't really like where I put it, so you draw it again. It's fine to draw more, but you don't need them all for sure. What I know is that this whole thing is 6, and I know that these are congruent, and then I need the central angle here, which is 360 divided by what? 6, which gives me 60 degrees. Okay. So now I take that entire triangle that I drew, okay, the entire thing, and I'm going to redraw it outside of my polygon so I can do some stuff. And I say this because your polygons sometimes are very small and you don't really have room to do things inside of there. And this whole thing is 60. All right, so what I'm looking for is the apothem. Now, this is an isosceles triangle. Therefore, what happens to the base of the triangle? Since this is perpendicular. It gets cut in half. So if this is 6, this is 3, this is 3, right? This whole big angle up here is 60, so each one of these is 30. So do you have enough information to find the apothem? Yes, because we're going to look at this little right triangle right here. And you can label if you need to, but I would say we probably don't really need to. This is 30, so this is S. This is 2S. This is S times the square root of 3. So what is the apothem? 3 square root of 3. See how easy that is? Just a matter of labeling it. Okay, so I'm going back up here, and I'm going to plug this in. This is going to give me 1/2 times the apothem, which is 3 square root of 3, times the perimeter, which is 36. So I would say let's take half of 36. What's half of 36? 18, and you don't need your calculator. Then 3 times 18 would be, 3 times 10 is 30. 3 times 8 is 24. So together that is 54. Square root of 3 meters squared. Okay. Questions about that? Okay, good deal. Now, even though we only used half of it, you still need to pull the entire triangle out, because one of the most common mistakes is not using the whole side length for that, so trust me on that one. What kind of triangle is this big one that I pulled out of here? It is isosceles. You can be a little bit more specific than that. Because if this is 30, what's this? 60, and this is 60. So that this entire triangle that's made up of the two radii are what? It's equiangular and equilateral, right? So what's the radius of this hexagon? 6, okay? Now, that does not happen in every single polygon, so you cannot just assume that they're all equilateral, because they absolutely are not. In this case, it is. All right, we good so far? Yes? Okay. All right, so let's look at B. Another area of a regular polygon. So area is equal to 1/2 apothem times perimeter. So your perimeter is equal to n times s. Do we know what n is? Yes, what is it? 6. Did they give us s? No. All right. Did they give us the apothem? No. Okay, so I'm going to have to go over here and go ahead and start labeling stuff on my polygon. I could draw this radius in, but that 10's kind of in my way, so I think I'm going to draw it over here instead. Got this. This is my apothem. This whole thing is my side length. This is 360 divided by what? 6, right? And what's 360 divided by 6? 60. Okay. So I'm going to take this whole triangle, because I don't really like it sideways, and I'm going to draw it over here. So this is the apothem that I need. This whole thing is 60, and this is 10. Okay. So that means that this is 30. So here I have a 30, 60, 90 triangle again, right? And that makes it not so bad. What is, if this is 10, this is 30, so what is this? 5. And what's your apothem? 5 square root of 3. Okay. So when I come back over here to finish finding the perimeter, what is S? 10. This whole thing is S. It is 10. Because if this is 60, this is equilateral again, but that's only because it's a hexagon. That only happens in a hexagon because you get 60 as the central angle. So just keep that in mind. So I'm going to get 6 times 10. So the perimeter is 60, right? Easy to find, but you had to find the side length first. So I come over here and plug it in. 1/2, I already found the apothem. It is 5 square root of 3 times the perimeter, which is 60. Totally don't need your calculator. Half of 60 is 30, and 30 times 5 is what? 150 square root of 3 inches squared. Okay. We good so far? Any questions? All right. Let's look at C. So again, we start just like on everything else. Area is equal to 1/2 apothem times perimeter. Perimeter is equal to n times s. What is n? 5. Did they give me s? Yes, so this is 5 times 4, so perimeter is 20. Super easy, but write it down so you don't use the wrong number. Okay, so I'm going to come back over here. Again, I could draw my triangle over here, but I think we kind of like it better when it's right here in front of us. This whole thing is 4. These are congruent. I need my apothem. So I need to find the central angle. That's 360 divided by what? 5. And what does that give me? 72 degrees. So then I'm going to take this and redraw it out here. So I can draw it a little bit bigger. And I get this whole thing is 72. This is 4. This is A. So is the radius 4? Is this side length 4? No, radius is not 4. I don't know what it is, but it's not 4. If this whole thing is 72, then that makes this piece 36. So is this a special right triangle? No. Do I know anything else about that triangle that I don't have labeled? What is this? This is 2. Now, I do not care about the angle. Do not even bother with that angle because chances are pretty good somebody's going to subtract it wrong, and we do not want to go there. So I do have this, though. This is 2. All right, so it's not a special right triangle. Can I do Pythagorean theorem? No, because I don't have enough information. So what do I need to do here? Trig. Yeah, your other option is trig. So this is my angle. This is the angle that I use. Do not go and even find that one. Not even worth it. This is your opposite. This is your hypotenuse. This is your adjacent. Which one do we not care about? Hypotenuse. You really are not going to care about the radius at all unless they give it to you and you have to use it. You don't need it to find anything. So if I'm using opposite and adjacent, which trig function is that? Tangent. So I'm going to have the tangent of 36 is equal to the opposite, which is 2, over the adjacent, which is A. The variable's in the denominator, so what do? Flip them, right? So A is equal to 2 divided by the tangent of 36. What do we do when we get to the calculator? Make sure it is in degree mode, yes. Okay, so check your mode, mine's in degrees, so then we're going to do 2 divided by the tangent of 36. It's a crazy decimal, which doesn't surprise us, right? So we'll store this, we called it A, so I'm going to store it in alpha A. So that's 2.7 something, something, something. So I'm just going to write down A equals 2.7 dot, dot, dot. Because that kind of reminds me, I am not typing that decimal back in. You do not type a rounded number back in. It is stored in the calculator. So when I come back up here to plug things in, I'm going to get 1/2 times the apothem, which is 2.7 something. That's just a reminder to me to use what's in the calculator, right? Times the perimeter, which is 20. So I don't have to simplify anything before I put it in the calculator, but it would actually save me some keystrokes because taking half of 20 is super easy, right? So I could just, in my calculator, then do 10 times A, and that gives me my answer. Okay. So that means that the area is equal to 27.528 inches squared. That's what you need your calculator for, not for the other stuff. Questions? This isn't bad. It just combines a bunch of stuff you already know how to do. You just got to be able to label it correctly, think about what your angles are, think about what your options are to apply, and so forth. Any questions? All right. Then let's look at this next one. Maybe. Just thinking about it. There we go. Okay, so this is a triangle. If this is a regular polygon, then what kind of triangle is it? Equilateral, equiangular, right? So we know how to find the area of a triangle. It's 1/2 base times height. There's also a formula specifically for equilateral triangles that we haven't talked about yet. But you can also treat it as a regular polygon if it's actually a regular triangle. And so my suggestion to you is that if you are given information that lends itself to a regular polygon, like for instance here, what did they give us? what part of the triangle did they give us? The radius. So they gave me the radius, which has nothing to do with base and height, right? But that's more of a regular polygon thing. I would say it's going to be easier to go down that road than to try and force it down base times height. Okay, so we're still going to treat this as a regular polygon. So area is equal to 1/2 apothem times perimeter. So perimeter is equal to n times s. What is n? 3. Did they give us s? No. Okay, so we're going to have to come back to that. So just like in any other regular polygon, I'm going to come over here and I'm going to draw in the 2 radii. One of them was already there. Draw in, I need my apothem. I need the central angle, which is going to be 360 divided by what? 3. What does that give me? 120. Good. So then I take this triangle, just like all the rest, and I'm going to redraw it outside of this. Now you got to keep track of what's what, because this is a triangle that you're taking out of a triangle. So remember, the whole side length and perimeter, we're always talking about the original figure. So I'm going to draw this in. This is my apothem. This is 14, which means this is 14. This whole thing is 120. So if that whole thing is 120, that means this is 60. So this right here, I have another little special right triangle, but pay attention to the fact that the 60 is in a different player. That was 30 when it was the hexagon, right? So the things are arranged a little bit differently. So if this is 60, that makes this 30. That means this is s, 2s, s squared to 3, right? So what's the apothem? 7, and this is 7 squared to 3. So what is the side length of the original one? 14 squared to 3. Again, that's why I have you draw this whole thing out here, because the very common mistake is to use that as a side length. That's the side length of this triangle, but that's only this part. I don't care about it. I need this whole thing, which would make that 14 squared to 3. Okay. So I come over here then, 3 times 14 squared to 3. You no longer need your calculator. What's 3 times 14? 42. So this is 42 squared to 3. So then I plug this in here, and I'm going to get 1/2 times the apothem, which is 7, times the perimeter, which is 42 squared of 3. So half of 42 is 21, so 7 times 21 squared of 3. 7 times 21 would be what? 147. So your area is 147 square root of 3 centimeters squared. Questions? It's totally something you're capable of, right? But drawing, labeling, thinking about what you have and what you've found, super important, because if you get lost in your own work, that's what makes it the most difficult. All right, so let's look at these pictures down at the bottom here, because this is some things I want to talk about that kind of come up in here. If I draw this in, what part of the triangle is that? That is the radius, okay? And if I draw this in, what part is that? Just the pink part, the apothem, right? So sometimes people will say, oh, well, I have the radius or I have the apothem. I'm just going to double it to get the height. That doesn't really work that way, right? Because these two together are what actually make the height of the triangle. So the height of the triangle is the radius plus the apothem. But we really don't even care about that. But I'm just showing you that so you don't try and do something weird because you think, oh, well, I can still just do base times height and I'll just double the apothem or double the radius. That's not what's happening. You with me on that? Okay. So then over here, if this is a regular polygon, what is this thing? A square. So if I draw this in, what part of the square is that? The apothem. And this right here is what part of the square? The apothem also, right? So then the entire side length of a square is really just 2 times the apothem. Is that true for a triangle? No. Is that going to be true for any of the other ones? No, just for the square. Okay. All right, so then let's look at this one. We're going to draw some different parts in here. If I draw this in, what is this? Radius. And then this is the radius. So since this is a square, that means all the sides are congruent, and these are right angles. So what kind of triangles do I get when I draw in both radius? 45, 40. Yeah, these are isosceles right triangles. So isn't this 45 and this is 45? That make sense? Now if I draw this in, what part of the square is this? This is the apothem. And do you see how the apothem makes another smaller 45, 45, 90 triangle here? Okay. So again, if you understand the relationships and think about what you have, some of this stuff is just real easy and it's all about labeling. You don't have to go do any crazy stuff anywhere. All right, so then let's look at this one. If I draw this in, this is the radius, right? Draw in the other radius. Then I want to find the central angle, so that's 360 divided by what? 4, which gives me, what does it give me? 90. So this is a right triangle as well, which means this is also 45, 45, 90, which means the side length of the square is what? Got a 45, 45, 90 triangle. This is R square root of 2. Exactly. Because this is a 45, 45, 90 triangle. So every time in a square, the side length is the radius times the square root of 2. Every time. Okay, we all good? Any questions? All right, so there's just some special cases that come up. I just want you to see those relationships. All right, so go ahead and glue this in.